Hey guys, good morning. Unfortunately, I won't be in class today. I apologize for that. I had to make a doctor's appointment, and the earliest I could get was today during the school day. It's pretty important. My back's still pretty messed up, and they're recommending surgery for me now, and I'm kind of worried about it. So I wanted to get some opinions as soon as I could, get this straightened away, so I could move on with my life. You know what I mean? Anyway, today we're going to be starting something pretty interesting. It's definitely different from anything that you're used to in math class. Um, we're basically going to be doing no traditional number math today. It's an introduction, I think, like just a grain on the beach of this idea called logic. Okay, in college, I took courses and courses on this stuff, and it gets very interesting and very complicated, and it doesn't even look like the math that you're used to seeing. Um, Let me just introduce you to the idea with starting with one of my favorite characters in all of American cinema, um, Mr. Spock, or um, the science officer Spock. Anyway, he says logic is the beginning and not the end of wisdom. And that's what we're studying today, this idea of logic. Okay, specifically, we're going to be doing conditional statements, which are the beginning of this thing called logic. And this is a specific kind of logic called Boolean logic, and it gets very complicated. It governs things like how we organize and describe electricity. It governs things like how we program um, early computers and even today's computers, like structures of ideas and sets. Um, a lot of the binary mathematics we deal with. It's it's really interesting stuff. Obviously, we're not going to get into any of this stuff. But I just wanted you to understand that this is the first step into a world with no end, and which certainly does inform and structure the world which you live in, whether you realize it or not. People have built it, and we are just simply living on the top floor. Uh, anyway, we study this thing called logic in geometry class through the idea of the first step, conditional statements. Okay, conditional statements um, deal with language so much, not so much like with actual numbers. Okay, so there are laws governing the universe you and I live in. The vast majority, if not all of them, are mathematical, right? So like there are some things which are incontrovertible. You can't argue with them. Like if I have one marker and I add another marker to it, then I get two markers, right? There is no universe where I would take one and they add somehow to three. So there are illogical and logical things within the world, and not all of them can be described using mathematics. We're going to be looking at some which can be and some which cannot be. But in either way, there are laws which govern this world that we live in, and there are laws which govern the ideas that make it up. And those ideas we can organize into conditional statements, and they have specific rules that they follow and ways we can reorganize them and essentially like attack and treat ideas as a lawyer would. Like there are rules which make sense and which don't make sense, and oftentimes you'll find pseudo intellectuals trying to make arguments which fly in the face of actual logic, actual conditional statement logic. So let's get started. Um, the GNAT today is just a little thought, a little brain teaser here. I'm basically just thinking through this. So I want you to answer always, sometimes, or never. This is actually on Canvas. It will be on Canvas. You can answer these questions. So let's go ahead and break them down. Maybe I'll give you some pointers. So answer always, sometimes, or never. An acute angle and an obtuse angle are complementary. What's it mean to be acute? It means to be less than 90 degrees, right? What's it mean to be obtuse? Well, it means to be greater than 90 degrees. And of course, complementary means to be equal to 90 degrees. So you can go ahead and determine that for yourself. Is that always true sometimes or never true? All right. The next one says if two angles are supplementary, then they form a linear pair. Okay, so you got to ask yourself what supplementary means. Supplementary means, of course, get this chord out of here. This means to sum to 180 degrees. And a linear pair, what's a linear pair? A linear pair looks like this. Right, this is angle 1, that's angle 2. So linear pair are supplementary, but they're also adjacent. So think to yourself if this is always, sometimes, or never true. All right, this last one, if two rays are collinear, collinear of course means to be on the same line and share an endpoint, then they are opposite rays. Okay, you remember what opposite rays look like? They look like this. Okay, so answer me, is this sometimes, always, or never true? And that's your do now. Okay, so first we have a lot of, well, basically throughout the whole chapter, we have this section rather, we have a whole lot of uh, definitions. Now this is 2.2 in the text, but in our curriculum it's 3.1. So a conjecture. A conjecture is an unproven statement that is based on observations. So it's basically an educated guess. Educated guess based off observations, but it's conjecture, which means it remains to be proven. It's unproven. So a lot of times we use inductive reasoning to make those kind of conjectures. So you use inductive reasoning when you find a pattern in a specific case or specific cases, and then write a conjecture for the general case. So you're looking at one specific or a couple specific examples, and then making a generalization about a larger case. Let's look at an example here. Describe the pattern in numbers and write the next three numbers in the pattern. So this would be my specific case, and then this would be my conjecture, right? Finishing the pattern. Here are some more examples of what we can do when we make a conjecture. So the sum of any two odd numbers is what? So you're supposed to fill in this blank here. I want you to try and do that. Pause the video and try and do that. Now maybe what you did was come up with an example in your head, right? Two odd numbers. What's an odd number? Like 3 and 5, right? That's 8. Certainly, they don't want me to put 8 here. What do they probably want me to do? They want me to probably write, is it even or is it odd? Well, the sum of any two odd numbers looks like it's even. Now, it would take me a lifetime to do all the odd numbers, right? Because there is an infinite amount of them. So this is, again, an inductive reasoning conjecture based off of my one observation. The difference of any two odd numbers is what? So again, you have to make an example. If I wanted to actually prove this, this is not proven. This is just one example. It's what you would colloquially call anecdotal, right? Doesn't mean it's wrong. It just means it's not proven. If I wanted to prove it, I would have to use some serious mathematics, some serious logic, which we're not quite ready yet. So anyway, the difference. So let's say 5 minus 3 equals 2. And 2, well, it's actually, strictly speaking, 2 is not even, right? Oh, no, I'm thinking of prime. So yeah, 2 is even. We can split it into 2 again. So another even answer. Sometimes I get even and prime confused. All right, the sum of an odd number and an even number is, right, so an odd number is not divisible by 2, an even number is divisible by 2. So pick another example, right? Make an example in your head. What do you think? Odd number plus an even number. Looks to me to be odd. Right, so these are all conjectures based off of an example that we pull. Even if I have 5 examples it's still inductive reasoning. Okay, we're looking at specific cases, right? We're not looking at a generalized case because that would require us to understand some more higher level logic. So conjectures can be true or false. They can be true if I observe them to be true in every single case, which of course would take sometimes a lifetime. Um, and then it's false if I could just find one example where it's not false. I mean, where it's not true, rather. If you can show it's not true every time, then it's not true, period. So if a shape has two sides of the same length, okay, it must be a rectangle. Is this true or false? Think to yourself and put down an answer. Pause the video. So maybe what you thought up was an example. Maybe you were trying to make a shape with two sides the same length. First thing I think of is, since we've been in triangle land forever, I think of an isosceles triangle, which certainly is not a rectangle. Okay, so this would be an example where this is not a rectangle. So clearly we have a counterexample, something which shows this to be false, right? So this is clearly not true. This is false. I mean, I might be able to find an example where that is true, right? If I draw a rectangle, I have two sides the same length, right? That's a rectangle, but I found an example where that's not true. So I can't say this is always true. Okay, how about this one? The square root of 9 is 3. Okay, well, this is kind of odd because this is just a truism, right? I put this into a calculator. What do I get? I get 3. Is there any example where I can take the square root of 9 and it not be 3? Some of you guys might be thinking about -3. But that's a little bit of different of situation, right? Because that would be like saying the square root of 9 is equal to, well, really, we'd have to start out with this. X squared equals 9. X is the square root of 9. Then we know that X could be plus or minus 3, right? But we're involving a variable, and that changes it up a little bit, okay? I'm sorry if you can hear my daughter screaming up there. Anyway, um, however, there is no variable here. The square root of 9 actually is 3. So this is true. While it is a little bit confusing because of this, you can only apply this plus or minus when there is a variable present. And there isn't one. And so what we would say the natural root of 9 is 3. So this is actually true. As far as I can estimate anyway. All right, a circle drawn around a four-sided shape will always touch all four corners of the shape. All right, so just draw, I guess draw a circle. Do my best, draw a circle. It's not the best circle, it's pretty good. And so maybe you can try and draw a shape in there that has four sides that don't touch all the corners. One, two, three, four. Haha, there's a corner it's not touching. So I found an example where it's not true. So this is false. Okay, so this process, what we just talked about, of looking for an example where it's false, and showing that that statement, that conjecture, is actually then false, is using this idea of a counterexample. Hold on just one second. I'm going to see if I can just pause this video for a moment. I have to run upstairs. Okay, sorry about that. I was trying to find a way to get my webcam back on, but I couldn't really figure it out. Um, anyway, yeah, whatever. Okay, so a counterexample is a specific case for which a conjecture is false. Of course, my hovercam froze as soon as I started recording. All right, in the previous true or false questions on the last page, you just proved that not all conjectures are true. You did find at least one example to show it wasn't true, right? We went through that. Show the conjecture is false by finding a counterexample. We just did this, but let's go ahead and do it again. If the product of two numbers is positive, then the two numbers must both be positive. Okay, well, this is clearly false based on this counterexample, right? Negative 2 times negative 2 is positive 4. So here I have the hypothesis right at the beginning, but I have the opposite, or I have something which is not included in the conclusion, right? These are not both positive, so this is a false statement. It may sometimes be true, but it has to always be true for it to be actually true. All prime numbers are odd. Well, actually, this is where I was confused earlier. A prime number is a natural number greater than 1 that has no positive factors other than 1 and itself. A number factor is something which is divisible by, right? The only factors of 2 are 1 and 2, and therefore 2 is actually prime and even. And it's the only number that I'm aware of which is both prime and even, one of those exceptional cases. So again, one counterexample, that's false. If the product of two numbers is even, okay, then the two numbers must both be even. Well, I mean, sometimes that's true, right? 2 times 4 is 8. 8's even. These are both even. But I found an example, 2 times 3, where that's not the case, right? 3 is not even. So this is also false. Okay, so now we get into the meat of it here. A conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. A conditional statement, the big part here is the condition, right? It's based on a condition. So when a conditional statement is written, it's written in an if-then form. The if part contains the hypothesis, and the then part contains the conclusion. Feel free to pause and write this stuff out. I know it's a lot to write, but you're going to understand it better if it enters your brain through both your eyes and your hand. Okay, so here is the probably most used first example. If it is raining, okay, this would be the hypothesis. If it is raining, the conclusion might be then there are clouds in the sky, right? Can it rain without clouds in the sky? Um, I mean, I can't think of an example. I mean, if it's going to rain, you're going to have some clouds in the sky. You might get a rainbow with some sun as well, but it has to be at least partly cloudy. It just doesn't rain on a clear day, right? So this would be the hypothesis or the condition of which the conclusion depends, right? So if this, then that. Let's rewrite the conditional statement in if-then form for these following, okay? First, identify the hypothesis and the conclusion. And when you write the statement in if-then form, you may need to reword the hypothesis for conclusion. Okay, I'm going to cover up the answers so this becomes a little more interesting. The statement is all birds have feathers. Now, this is actually true. Believe it or not, penguins do have feathers. They're just like a certain type of adapted feather, which works well in the water. Anyway, can we write this in if-then form? What is the condition? all birds, right? The conclusion would be they have feathers. So maybe you'd want to, well, just try your best. Try and write this in if-then form. If what, then what? Maybe you wrote something like this. If an animal is a bird, then it has feathers, right? So hopefully you can see we have a hypothesis, right, or condition, right? And we have a conclusion, right? It has to have feathers. Now, I should have omitted this word then, because these are really kind of like the skeleton of the statement. Let's try again. Two angles are supplementary if they are a linear pair. So here the order looks as though it's been switched, right? Because this word if is pretty telling that this is the condition. This is the conclusion, right? How do I know angles are supplementary? Based on the statement, I know the supplementary if they're a linear pair. So I want to put this first. If two angles are a linear pair, then they are supplementary. Okay? So the condition here is they are a linear pair, right? That becomes my hypothesis. My conclusion is that they're supplementary. And again, I have that skeleton, that background template of if and then. If this feels weird and different to you, that's because it is. You haven't really thought about this stuff before. Okay. So we can also play around with ideas by taking the opposite of these ideas, or what we would call in mathematics and logic, the negation of a statement. Okay, so negation of a statement is the opposite of the original statement. So usually that just it involves adding the word not or removing the word not from a statement, taking the opposite of it. Sometimes you might see this symbol, which means to negate it. We use that symbol for similarity too, but that would also mean like the opposite of the negation of. So what's the opposite of the ball is red? Well, the answer isn't the ball is blue, right? The answer is the ball is not red. Okay, it's the opposite of it. What's the opposite of the cat is not black? That would be the cat is black. What did I do there? I removed the word not. Okay, so that's what we would call a negation. Okay, so verifying statements, right? This ties into all of which we've done. So conditional statements, these if-then statements, can be true or they can be false. To show a conditional statement is true, you must prove this conclusion is true every time the hypothesis is true. So this is very hard to do. You know, sometimes it takes generations or a very good mathematician to show in a general case it's always true. It's much easier to show a conditional statement is false. Why? Because you only need to give one counterexample. So sometimes we'll take a statement and we'll rearrange it using logical rules so that we get the opposite statement. And if we show that that's false, which is easier to do, well, then we know that the original statement is true. I know it's a little confusing, but we use the rules of logic to organize the ideas in such a way as to make our job showing that it's true easier by taking the opposite statement and showing it's false. That again gets into a little bit more complicated and heavier mathematics, which we probably won't deal with. But I just wanted you to know it's pretty powerful stuff, and people do use it. So here we get into the various forms of the conditional statements, right, and how we rearrange them and order them to get different varieties of the same statement. So the converse, all right, is when we exchange the hypothesis and conclusion. So what we typically do is we use this idea of P's and Q's. So we would say that the hypothesis is P, and we would say that the conclusion is Q. Hypothesis P, conclusion Q. Okay, just a little idea. And we use this arrow to indicate the word then. All right, so if P, then Q. Okay, and we'll use this symbology to kind of help us understand these. So the converse of the conditional is when we exchange hypothesis and conclusion, meaning P and Q are switched. So what would that look like? It would look like if Q, then P. Okay? So let's go ahead. I'm going to cover this stuff up so we don't think about it just yet. Let's look at this original statement. If angle A is 99 degrees, then angle A is obtuse. Hopefully we can all agree that this is a true statement. Now let's think about the converse. What if I switch these ideas? What will that be then? Excuse the funny coaster, by the way. Okay, so if A is obtuse, then angle A is 99 degrees. So this is the converse, right? We've switched it. Now we have Q first, and then we have P originally, based off the original. So think to yourself, is this true? Can you think of a counterexample? Hopefully you can. If A is obtuse, then A doesn't have to be 99. A could be 98. It could be 100, right? It could be many things. So this is actually a false statement. Okay? The inverse of a conditional statement is when you negate both the hypothesis and the conclusion. So negate, of course, means to take the opposite of, which we will just say is not. But we're going to use that symbology to show that in our notation here. So we keep the original order. We just say if not P, then not Q. Okay, if not P, then not Q. So think about what that's going to sound like here. The original statement was if A is 99, then A is obtuse. What would this sound like? Well, it sounds like this. Oops. I gave you the answer already. If A is not 99 degrees, then A is not obtuse. Okay? So again, this was if not P, then not Q. So can you think of a counterexample where A is not 99 degrees, but A actually is obtuse? Well, yeah, we just talked about it, right? 100 degrees. That's obtuse. So this is also a false statement. There's one last variety of what we can do to these conditional statements to rearrange them, and that's the contrapositive. And the contrapositive is really like both of these things combined. Okay, so if I took both these ideas and put them together, I'd get the contrapositive, which means if I both switch and I negate, then I get the contrapositive. So we have to switch them, right? Put Q first and then put P. And then we also have to negate both of them. Negate both of them. So that would look like this. If A is not obtuse, right? Took Q and we negated it and put it first, then A is not 99 degrees. Right? And think about this. Is this true or is this false? Can you think of a counterexample where A is not obtuse, but A is actually 99 degrees? And the answer is no, you can't. Right? Turns out that that's true. Right? If A was 99 degrees, then A would have to be obtuse. Right? So there is no example where this is false. So that is the introduction essentially into conditional statements. It'll take some practice, but there's a lot of worth here you probably won't be able to really appreciate the worth in conditional statements because, well, we simply just don't have time for the scope of this class. But maybe in college, if any of you guys do go into mathematics, which I hope that you do, or hard science, um, maybe you'll think back to this day when you first were introduced to it. All right, in your own words, describe how to write the following statements. All right, so the converse, you go back to the conditional statement and swap the hypothesis and conclusion. That's essentially it. Now, it's kind of silly for them to write this and then, just have you copy that. Maybe I should have you try your best to put it into your own words and not write those down. So try in your own words, describe how to write the statements. Those statements being the converse, the inverse, and the contrapositive. Okay? All right, so here we're going to do the same thing. All right, with this example. So write the if-then form, the converse, the inverse, and the contrapositive. I'd like you to pause the video and try your best to do this on your own. Okay, so we're given the first line, which is nice. This is clearly the hypothesis. You are a guitar player, God forbid. And this is the conclusion, Q. Okay. What would the converse be? Well, remember, the converse is when you switch them, right? We switch P and Q. So, oops. You put Q first, then P. So what's Q? You're a musician, so we'll write if you are a musician, then what? Well, I put P as the then, right? Then you are a guitar player. Okay, so is this true or is this false? If you think it's false, you have to provide a counterexample. So what's your counterexample? Well, can you think of a time when I satisfy the hypothesis, right, where this is true, but this last thing is false? Well, yeah. I mean, I'm a bass player, right? I'm a musician, but I'm not a guitar player. So this is false based off that one counterexample. What is the inverse? Well, the inverse is when I negate P and I negate Q, right? I take the opposite of them, but I keep the original order. So I'll say, if you are not a guitar player, then you are not a musician. Okay? Think about this. Is this true or is this false? Can you think of an example where this is true, but the conclusion is false? Well, yeah, the same thing I just said, right? I mean, I'm not a guitar player. However, I am a musician. Why? Because I play bass. So this again is also false. So the contrapositives, when we do both these things, we switch P and we switch Q and we take the opposite of them. So this would read, if you are not a musician, then you are not a guitar player. I guess like guitarist sounds a little bit weird. back when I was in high school, everybody and their mom played guitar. Um, I guess things have changed. I don't think I know any kids that play guitar these days. All too busy playing video games and making beats or whatever. That's true, right? There is no one who can say that they are a guitar player, but they're not a musician. At least, following the strict rules of this game. So you might notice a pattern going on here. True, false, false, true. True, false, false, true. And, you'd be right. That is essentially the pattern of ideas here. And that's always the case. It's pretty cool stuff, I think. So a conditional statement and its contrapositive are either both true or both false. They're always in agreement. Similarly, the converse and the inverse are either both true or both false. It's what we would call equivalent statements. Okay? In general, when two statements are both true or both false, we call them equivalent statements. They're the same thing, just the rewording of it. So you can write a definition as a conditional statement in if-then form as its converse. Right? The converse, if it's a good definition, the converse is also true. Both the conditional and statement and its converse are true if it's a good definition. For example, consider the following. If two lines intersect to form a right angle, then they are perpendicular lines. Right? I think we all agree. I can also rewrite that. The definition can be written using the converse, right? If you switch P and Q. What's P here? This is P. What's Q? Right here. So if I switch them, it should also be true because it's a definition, right? This here wasn't a definition, which is why we observed the true, false, false, true pattern. But if it's a good definition, it'll be true, 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 true. Like it is here, right? The converse here, if two lines are perpendicular lines, then they form a right angle. That's Q then P. That's also true. So that's good definition. All right, so a good definition can be written both in the converse and in the original, and that's what we call a biconditional statement. A statement that contains the phrase if and only if. You might want to abbreviate that using that fancy symbol IFF. It's up to you. When a conditional statement and its converse are both true, we can write that statement as a biconditional statement. Okay? If it's a good definition, it can be written as a biconditional. So let's take a look. If two lines intersect to form a right angle, then they are perpendicular. The converse would be, switch P and Q, if two lines are perpendicular, then they intersect to form I'm going to use the symbol, a right angle. The biconditional is when we throw the if and only if in there, okay? So we'll use the conditional statement as the beginning here. So two lines form a right angle, and then here comes the kicker. If and only if they are perpendicular. Okay? That would imply bidirectionality. That's the symbol for a biconditional right here. That's what if and only if means. It means, basically it goes both ways. All right, biconditional using the converse as the statement. Okay. That means I put this one first, right? Two lines are perpendicular. Then here's the biconditional part, the if and only if. If they are if they intersect at a right angle. Okay, so that's a good definition. Why? Because all of these are true. They all make sense. Okay, example 4. Decide whether each statement about the diagram is true. Explain your answer using the definitions you have learned. Almost there, guys, almost there. So let's decide if A is true. AC is perpendicular to BD. Okay? Are they perpendicular? Hopefully you're saying yes. Probably shouldn't have used red for yes. Yes. Now it's Christmas time again. Yes. Why? Because if AC is perpendicular to BD, then they are, then they intersect rather at right angles, which they do. Or I could have reversed that. If they intersect at right angles, then they're perpendicular, right? I probably should have written that in the converse. Probably should have switched P and Q. But yeah, that's true. How about B? Angle AEB and CEB are a linear pair. Is that true? Well, yeah. Actually, here it is true. Um, we didn't really talk a whole lot about the linear pair definition here today, but if they are supplementary, which appears they share a common side, and their non-common sides form opposite rays, well then they are a linear pair. So this is the conditional type of thinking you have to go through. If this, then that, right? It's kind of teaching your brain how to order information. So the answer here would be yes. If two angles share a common side, right? Like EB here, and the non-common sides, right? These are the non-common sides, EA and EC. If they form opposite rays, then they are a linear pair. All right, so I've satisfied the definition. I've satisfied the condition. All right, EA and EB are opposite rays. Is this true? Do they share an endpoint? Yes. Are they collinear? No. So we haven't satisfied all the conditions. So the answer here is no. What condition have we failed? Rays are not collinear. Okay, so I failed to meet one of my conditions, the hypothesis of my definition. So this is not satisfying the conclusion. So it's false. It's not an opposite ray pair. All right, just a quick recap. All right, a conjecture is an unproven statement based on observations. Inductive reasoning is when you look at a specific case or specific cases and you write a conjecture generalizing the generalizing the case, right? A counterexample is a specific case for which a conjecture is false. We found counterexamples when we wanted to show a conjecture was false. The conditional statements are when we throw statements into a specific form, an if-then form, where we have a clear hypothesis and a clear conclusion. When a conditional statement is written in if-then form, the if is the hypothesis, the then is the conclusion. And the negation of statements, the opposite original statement, we usually input the word not in, or we subtract not if it already has it in. Okay, we learned that the converse is when we just switch, right? The converse is when we write Q and then P, right? The inverse is when we keep P and Q in the same order, but we take the opposite of P and Q. The contrapositive is when we do both these things. We switch them and we negate. All right, and then we realize that the conditional and the contrapositive are equivalent statements, and that the converse and the inverse are equivalent statements. And what's cool is it doesn't matter what you put in there. It's always going to be like that, no matter what idea we're talking about. If two lines intersect from a right angle, then they are perpendicular lines. Well, kind of already knew that. And a biconditional statement is a statement that contains the phrase if and only if. Otherwise, you could write this fancy if like that. All right, I know that was a lot, guys. You're not going to 100% grasp it the first time. We'll hit some examples coming up, and it'll become a whole lot more clear to you. But we'll be using this when we talk about definitions in the future, when we introduce certain theorems. We'll discuss like the converse of them and things like that. Okay, so that's it. Take these notes down. I know it's a lot of writing. Do your best and turn it in. Okay, at some point today. And let me stop this.